So I'm gonna go very quick here what we talked about last time. We said that we might have a building like this, and we start talking about the ground elevation. And then we start talking about the first floor elevation, FE. And we said that sometimes that the two elevations are different, and this is very important quantity in flood risk analysis. Since if we have flood depths, mainly the damage is happen above the first floor elevation where most of the expensive component is. However, in some buildings, sometimes there's some valuable items like the mechanical systems, electrical system are below the first floor elevation, okay? So we spent the whole lecture last time trying to find out how to quantify the flood depths for each building for the entire community. You have data for every building. We were able to show you how to extract the ground elevation from a digital elevation map, and then how to extract the flood depths from a flood depths hazard map. We did this for Galveston County. And if you have the FFE value, that's good. If you don't have it, sometimes we use the foundation height to find the value of the FFE. Like let's say that the building has a foundation height of 3 foot. So you put the ground elevation from 3 foot so that you can get the FFE. And if you want to find the flood depths above the FFE, you get the water surface elevation to find what is this difference is. So water surface elevation minus FFE is going to get you the flood depth. That is the first important parameter that we need to do our vulnerability analysis, okay? So let's say we understand this concept very, very well, and we know how we get flood depth. So the next step is, I want to use this flood depth in a function that can tell me how much this building is going to have damage. Let's say, okay, I'm going to put this building here again. This is for hazard. Here I'm going to do vulnerability. And let's say this is my first floor elevation, and I have a few steps here to get here. I'm not interested in elevations right now. But I want to find out if this building got exposed to this flood height, how much damage I'm going to have here. First, you need to find all the components that got covered by this flood depth. Like let's say that you, for example, you have, I don't know, like a TV, a table here, and then a TV here, and then you have, I don't know, a couch here or something. You have tables, like table here or something. So you have a lot of components inside the building. You have a fridge, you have appliances, you have electrical component, you have a structural, non-structural components. So there is lots of components that are vulnerable. So the thing is, you need to make a list with all the components inside the building. It's gonna be something like this. Table, this table, you are gonna have component number 1, component number 2, until component number n, or component number 100 or 60, okay? Every row here is gonna have, for example, maybe cabinets, appliances, let's not say appliances, let's say fridge, stove, washer, dryer, doors, windows, electrical switches. Every component inside the building, we are gonna have them in a table. I'm gonna give you this tip. You're not gonna develop, but you have to understand the way to develop fragility. You have to divide a system into components. Let's say I'm gonna develop a fragility function or a flood fragility function for an electrical power substation. I never did that before, but let's think about it. I have to have a model, or I have to have a full understanding of the components in the electrical power substation, and then divide them each in a separate component, and study each component separately, how it is vulnerable to flood. Let's say that we want to study the seismic impact on this building. I have to divide this building into components: columns, beams, frames, foundation, and then I study how this hazard is going to impact every element. And once I know the performance of every element, I can have a full idea on how the building is performing. Okay, let's say that I put them in a table, component number 1, 2, 3, until component number n, okay? So here, you have to have an idea about the resistance of the component, okay? So right now I divided them into components. Right now, once I knew the components, I wanna know what is each component resistant to flooding. So you need to have an average resistance. Like let's say, we talked about this before. We want to find out what is the resistance of this laptop or this screen or this table to the flooding. So this laptop, as soon as the flood didn't touch this laptop is safe. So if the flood did, like let's say 1 foot, 2 foot, it's still safe. Once the water touched the laptop, it's gone. Okay? So the resistance depends on the elevation of the laptop. So there's some components based on their elevation, they are gonna be safe or not, okay? So let's say this TV, as soon the water didn't touch this TV is surviving. But the thing is, there's uncertainty in the level of this TV. This TV might be on a table, like this, might be mounted here at 6 foot or something, or might be here. So there's a huge variation. So that's why we go to something is called upper bound and lower bound of the elevation. So we put here lower bound and upper bound. So let's say we are talking about the TV. The lower bound of the TV, the elevation may be 0.6 meter, but the upper bound may be 1.5 meter from the ground. So that's here or here. Definitely the TV is not gonna be 10 meter from the wall. So that's for sure. And definitely it's not on the ground. Nobody put the TV like on the ground. So it's definitely a little bit elevated. So that's what we call upper and lower bound. Same thing with the replacement cost of the component. Like let's say this is the depth. Let's do the same thing with duration. And also the same thing with loss or cost. Let's put cost rather than loss. Right? Okay, so for the duration, there's some components that are very, very sensitive to water. Once they get touched with water, it's gone. There's some component, they have a little bit of tolerance. So maybe some of them, they can last an hour, some of them, they can last a day, some of them, they are not sensitive to water. Like let's say that the water is 1 inch outside your home and it made it inside and your flooring is wet. Maybe you will be able to dry this water. If you were able to dry it in 1 or 2 hours, you might not end up having no damage. But if you left this water for the next day, maybe you will have, the cabinet is gonna get wet. Whatever. So the wood stuff, maybe they have much more tolerance to water more than the electronic. The electronic, if they got touched with water, maybe in a minute, 2 minutes, 3 minutes, they are gone. Depends on if the water touches the sensitive component inside the thing. Like if it touch a processor, touch something that is very sensitive. Like let's say the fridge. Maybe the fridge can tolerate water, but once the water hit the compressor of the fridge or the electronics in the fridge, it's gone. So it depends on how long did the water last. So we need to put the upper and lower bound of the duration as well. Like let's say here lower and upper. Let's say 0 to 0.5 hour. Some component is gonna have 2 to 6 hours. So that's for the duration. Same thing for the cost. Like let's say the cost of an appliances. Is all the fridges have the same cost? No, some of them are cheap, some of them are expensive. Some people would actually, and also, like let's say in the same neighborhood, people would buy cheap fridges, people would buy expensive fridges, depends on your preferences. Same thing with not even, maybe the same appliance, from city to different city, it's different. From even in the same city, from vendor to different vendor is different. So there's also always upper and lower bound for the cost, and there's lots of websites like Home Advisor can give you how much the American families are spending on buying fridges or spending on painting their homes. So you can get an upper and lower bound of the cost of each component. So you might have also lower and upper bound. But why we are getting upper and lower bounds? The thing is, there is nothing in the literature that tells you what is the mean and the standard deviation of the resistance of these components. So that's why we are looking for a way that we can develop a mean and a standard deviation on their own. So the thing is, there is a rule. Okay, if you know the upper and lower bound of something, do you know how can we get the mean? Like if I told you this, either the lowest cost of replacing this table $100 and the highest cost is $1,000, what is the mean?
550.
Yeah, it's 1,000 plus 100 over 2. So it's the upper plus the lower over 2. 100 plus 1,000, so 1,100 over 2, so it's 550. All right, the standard deviation, there is a rule of thumb for a standard deviation if you know the upper and lower bound of the replacement cost or not the replacement cost of a specific parameter, it's equal to the upper minus the lower over 4. That's something that if you don't know the standard deviation, that's the closest to it. Okay, so we use a rule like this. So based on the upper and lower bound of the replacement cost, or either the depth or either the duration, like the depth resistance or the duration resistance, we can get mean and standard deviation. That's what we need. Okay, that's what we need when we trying to develop fragilities. We need the statistical parameters, and I'm going to tell you why we need the statistical parameters. The thing is, before, if you guys remember, to get mean and standard deviation, how we can do that? We need to collect data, right? Like, let's say that I want to know the mean and standard deviation of the compressive strength of the concrete. So what we do, we grab a lot of concrete cubes, we take them to the lab and test them and measure the compressive strengths. And we have the compressive strengths for multiple samples, we get the mean and we get the standard deviation, right? The process here is kinda the reverse process. We don't have samples, we don't have anything. So that's why we rely on knowledge-based data. Like based on our best knowledge or the best engineering knowledge, we know that this is the upper and lower bound, and then we were able to get mean and standard deviation. All right, so let's say that we already have the mean and standard deviation for each component. Right now, what I wanna do, I wanna get, let's say I'm gonna pick one component, a TV, all right? This TV. I wanna have a fragility function that has the flood depth on x-axis, like let's say this is D, and I want to have on y-axis the probability of failure. It's gonna be look something like this. All right? Definitely not curved like mine like this. Usually electronics, their curves are something like this, like a straight line or something like this. Why? Because there's no high uncertainty in their damaging. Like if you know, it depends on their elevation. But if you are sure about the elevation of the TV, it's gonna be here. Like let's say at 1 meter, all right, that's the mean. Once it gets touched with water, it's 100%, almost 100%. But if there is high variability in the height of the TV, let's say that the TV may be at 0.6 to 1.5 meter, this curve is gonna be something like this. Like it starts to damage from 0.5 meter or 0.6 meter, and then the end of the damage, it's gonna be at 1.5 meter, and then it's gonna reach the 100% here. Did you guys understand that?
Yeah.
So it's gonna start getting damage at 0.6 meter with probability of failure maybe very low, and then it's gonna get higher as soon as the water depth. But once the water depths reach 2 meter, there's 100% probability that the TV is gonna be damaged because it's gonna be covered. All right? Okay. So this is the fragility curve. But the thing is, how we can draw this curve? We need points. We need points on this curve so that we can draw them. The thing is, to do this realistically, we need to go to homes that got damaged from flooding, like let's say 1,000 homes, and make some measurement and find out what is the flood depths and the TVs that got damaged. Like let's say this home had a flood depth of 0.75 meter, their TV got damaged, so I'm gonna collect this data for maybe let's say 1,000 buildings. Once you have this, you can put the flood depths that you measured, and if the TV failed or not, so you are gonna, if it didn't fail, so you're not gonna put it here, because if it didn't fail, so it's not here. We only capture the failures. So, and then you are gonna have some points, some houses that got 1.5 meter, they got damaged. Some they didn't. So I'm gonna put all these points, and then I'm gonna draw a curve from these points. Try to fit a curve with these points. But the thing is, it's not easy to get this data. So how we can generate this data? We use a process that's called Monte Carlo simulations. Monte Carlo simulation is a reverse process of this one. This one, you have data and you get the curve. The thing is, I don't have this data, but I will be able to generate them. How? Monte Carlo simulation, basically, let's say you have the mean and sigma, okay? This mean, mu and sigma. Like let's say flood depths, you have upper and lower bound. You use mean and this rules to get the mu and sigma for the flood depths that this TV is gonna get damaged on. And let's say that you find mu and sigma. Let's say, for example, let's say 0.7, and here's 0.3, right? So, and then these numbers are gonna go into a black box. Well, it's not black box, it's a Monte Carlo simulation. So, Monte Carlo simulations, you are gonna tell this black box, I want you to generate 1,000 sample from using this mean and standard deviation. You will define what is the number of sample. Let's say n simulations equal 1,000 or 100, whatever. So the output from this simulation is going to be something like this. It's going to generate you a table like that, and here you are going to have the n simulation, and here you are going to have the generated flood depth. Let's call it, or the, yeah, okay, let's say component depth or component elevation. All right, so you're gonna have simulation number 1, 2, 3, up to 1,000. Let's say 1, 2, 3, up to simulation number 1,000. And this simulation is gonna generate, let's say you told this Monte Carlo simulation, the mean and the standard deviation of the height of the TV is 0.7 and 0.3. So it's gonna develop like something like 0.4, 0.6, 0.71, 0.81, 0.91, or 2, and a lot of numbers. If you take this 1,000 simulation developed by the Monte Carlo simulation, if you take their mean and if you find their standard deviation, it's going to be exactly these two numbers. So basically, Monte Carlo simulation is going to generate a synthetic data based on the mean and the standard deviation, so it can mimic the process that you have sampled. So I told you, you go to the lab with a 1,000 concrete cube, and you test them and you break them, and you collect this data. You are going to have a 1,000 information about these cubes. You take their mean and standard deviations, and you get this number. The thing is, Monte Carlo simulation is the reverse. You give it the mean and standard deviation, it gives you the data that is going to generate the same mean and standard deviation. All right? So right now, Monte Carlo simulation helped me to generate 1,000 elevation of this TV. So basically, it saves me the time rather than going a 1,000 home and take measures. Hey, if you know the mean and standard deviation, this is 1,000 random number. By the way, all these numbers are random, okay? But the thing is, you have to tell the Monte Carlo simulation what is the distribution of the data. Do you want a low normal? Do you want normal? So right now we are talking normal. So I'm gonna generate this data. But I'm gonna do a little bit of tweak here. Why? Because when you generate this with normal distribution, the thing is, he's gonna generate the data like this. Let's say it's gonna be something like this. The mean, like once you plot this data, the mean is gonna be 0.7, the same mean that you give it to him, all right? But the thing is, he's gonna generate data all the way up to negative infinity and positive infinity. So you will end up seeing some numbers he generated that the elevation of the TV is negative 0.2. maybe you will find it very far here, -0.2, -0.6. Does this make sense? The TV. So the thing is, there is no negative. There is no way that any component can be under the ground. So the first thing, we had to make a condition. If he developed a negative number, we take the absolute so that we can make it positive, all right? That's one thing. The second thing is, we know that there is an upper and lower elevation. There is no way, I don't know, maybe very, very low chance that the TV is gonna be at 0. So sometimes if you want, you can convert this normal distribution to something called truncated normal distribution. What is the area under this curve?
1.
It's 1, right? So the thing is, if you truncate this, like let's say that you know that the upper and lower bound, let's say it's 0.3 and the upper bound is 1.5, okay? You know for sure that there's no way that the TV is gonna make it here, or there's no way that the TV can make it here. There's a low chance, okay? But if you wanna keep it, you can keep it. But let's say that you know for sure that there's no way that there will be any elevations in this area. You can truncate this normal, but the thing is, if you eliminate these two pieces, the area under the curve is not gonna be 1. There is a way that you can do this in MATLAB, and I might show it to you, that you can develop a truncated normal distribution. This curve is gonna go up a little bit, something like this. The area that he went up, it covers the area that was a little bit around. So there's a publication that I have, it's gonna show this concept a little bit. So I'm just showing you how we do the whole process. So number one, we use the Monte Carlo simulation to generate a random numbers of the elevation of the TV. And by the way, this process works for wind. Like let's say we wanna find the impact of the wind on the roof shingles. Okay, do you guys know the roof shingles?
Yeah.
Or the roof panels, whatever. So the thing is, you can't go to buildings after wind and know how much wind speed that each shingle got to make it damage. That's impossible, right? Unless you have a sensor at this shingle and this sensor survived after the damage. So what we do is, we generate 1,000 number of the resistance of the shingle. We take the shingle to the lab and test a few of them, and we get mean and standard deviation. We cannot get 1,000. But maybe we take a few of them and you test them in the lab, what is the wind speed that they get damaged at, and take some measures, and based on mu and sigma, we generate 1,000 simulation of the resistance of the shingle to the wind speed. So that's one way to do it. All right, so let's say I already have the measurement of 1,000 elevation of the TV. I want to know the probability of failure of each one of these at each flood depths. So that's what we do. We divide, like let's say that we want to know up to flood depths 10 meter. I divide the 10 meter to 100 beats, or maybe 1,000 beats, whatever you want. Like let's say I'm gonna divide them every 1 centimeter. So I'm gonna have 1 meter, 2 meter, 3 meter, up to 10 meter. If you wanna do it by meter, it's gonna be very coarse fragility. So we usually make it 1 centimeter or 2 centimeter, whatever you want. Anyway, the code is gonna run. You're not gonna do this calculation by yourself, so you can't divide it into 100 or 1,000 beats. So let's say we are gonna look right now by 0.5 meter. Okay, every 0.5 meter, we're gonna see what is the probability of failure and make point. 1 meter, I'm gonna make point. 2 meter, I'm gonna make point. So, all right, let's say I wanna know what is the probability of failure. I'm gonna make another table here. And I wanna know the probability of failure. The thing is, you have to find the probability of failures at each flood depth. So you will take, let's say, this house, or this 1,000 house, was because every one of these simulations represent a component in a different house, okay? Let's say this 1,000 house was exposed to a flood depth 0.5 meter. Did this component fail?
Yes.
Right, it failed. Why? Because the elevation of the TV is 0.4 meter. Did this component fail? No, because it's up. This is no, this is no. So what we are gonna do, we are gonna count the number of fails. At flood depths equal to 0.1, flood depths equal to 0.2, 0.3, 0.5. Then at each one, I'm gonna count the number of fails, and then I'm gonna get the probability of failure. How? once you do this for all these TVs, like let's say this one failed, and this one not failed, this one failed, this not failed, this failed. You will count the number of failures out of the whole 1,000, and then we are gonna divide them by the number of simulations. Like I have 1,000 building, 500 got damaged from a flood depth 0.5 meter. What is the probability of damage? 0.5. 500 over 10,000 over 1,000, so it's 50%. Let's say the flood depths, the next one, 0.6 meter. I got 600 building got damaged, so the probability of failure 0.6. Let's say flood depths 2 meter. All that 1,000 damaged, all the flood depths is more, so that means 100% damage. So once you do this, you will get the, by the way, we are checking the failure of all the components at each of flood depths. Like you are gonna have for flood depths 0.5, flood depths 1, 2, 3, 4, 5, 10. So you are gonna have multiple one of these. Okay? And then at the end, you will get the probability of failure. Like if the flood depth is 1, the probability of failure 0.2, and then 0.31, and then 0.45. And then you will get the probability of failure at each of flood depths. Like let's say here's the flood depths. The flood depths, let's say it was 0.1. Sorry, flood depths equal 0.1. And then you will find if it's failed, 0.1 is not failed. So this is not failed. This is 1. This is 1, 1, 1. So the probability of failure is 0. Then at flood depths 0.2, all of them are gonna not fail. So all of them are gonna be 1. But at some point you will have flood depths equal to 0.9. So this is fail, 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 not fail. Okay? So then you count the number of failures, divide them by the number of simulations, then you will get the probability of failure. Did you guys understand this concept? Okay? So that's how we calculate the probability of failures using Monte Carlo simulations. All right, let's say here's the depth, here is the probability of failure. Let's say that you counted the probability of failure corresponding to each of flood depths. Like you end up having a table, and this table have the flood depth here and has the probability of failure here. Like for flood depths 0.1, the probability of failure 0.05. Flood depths 0.3, the probability of failure 0.15. Up to flood depths 10 meters, the probability of failure equal to 1. I'm gonna put this points here. So this points is gonna be something these points is going to be something like this, all right? But the thing is, they are usually like continuous, not like this. Let's they are continuous. Like when you draw this fragility, it's going to be something like that, like a random curve, all right? But the thing is, when we do our analysis, that's a lot of points. That's a 1,000 flood depths and 1,000 probability of failure. When we do our research at the community level, we don't need all these information. We need to reduce this information. So what we do, we curve fitting this curve. We do something that's called log normal fitting. And when we do the log normal fitting, this curve is gonna be fitted like this. This is the fit. It's gonna be something like this. When we log normal fit this curve. So we call this the raw fragility without any fitting, and this is the fitted fragility. And when we fit this fragility, it only gives me two numbers about this curve. This curve is gonna be having a parameter is called lambda and a parameter is called xc. The logarithmic mean and the logarithmic standard deviation of this curve. This is a cumulative log normal curve, has lambda and xc when we fit it. And when we look at papers, the papers always be something. Let's not talk about papers right now. Let's stay at the components. All right. I'm gonna talk about the paper in a few seconds, so I don't want to distract you. All right. So I have this curve. By the way, this curve is for a building or a component? One component, we only looked at one component. We have to do this for every component within the building, and this includes appliances, furniture, structural, non-structural, content, everything. So maybe some buildings have 50 components, some buildings have 100 components. We have to have this for all the components. Let's say after we did this, and let's not do the fitting right now. The fitting is at the end when we finish all the components. Let's say component number 1 was like this. All right, one curve. And then you did this for this table, and this couch, and this TV table. So you will end up having all these curves. Some components are in the second story, so you will find some components here. Some components are appliances, so there will be all vertical lines. And some components like the roof is gonna have something like this. You will end up having, you guys remember these curves when I was presenting the first presentation? So you'll have a lot of components like this. And all these curves coming from all these processes, okay? All right, so let's say I have all the components. The thing is, if I'm doing one building, I'm fine to deal with that. Like I'm interested to find what is the probability of failure for each component. But if I'm dealing with a community that has 1 million building, I'm not interested in the components within the building. I want to know one number about each building. What is the damage state? So we need to convert this 100 curve to a smaller number of curves that can represent the building. So what we do is, we develop something, it's called damage states, if you guys remember. Something like this. This is the damage state. Let's say we're gonna have damage state 0, damage state 1, damage state 2, damage state 4. And then you are gonna have a description of these damage states. And by the way, most of the literature, they have well-established damage state definition. Like if we go at FEMA, they have a standardized damage states for building. Like we call that this building has a slight damage if a specific components got damaged. We don't have to do our own unless there's no standardized damage states, okay? So when I was trying to do this in my research, I was looking if there's damage states out there. There was, like, the damage states are known, like there's insignificant, slight, moderate, extensive, and complete. That's damage state for any hazard. But how everyone is defining them based on the hazard, like in earthquakes, like we look at the cracks widths. So if the crack width looks like this, that's damage state 1. If the crack width like this, it's damage state 2 or something. But when it comes to flood, we need specific components that we can tell if this component is damaged, so that's damage state 1. If this component is damaged, that's damage state 3. So these 100 components need to be assigned to each damage state. Like let's say if the building doesn't have any damage inside and all the damage from the outside, that's insignificant damage. You can live in your home. If damage state 1, let's say if your carpet is wet and your flooring has maybe 1 inch of water that cause damage or make the floor wet, so you have to do some work to dry the floor, so that's damage state 1. But if the water is like 1 feet and this 1 feet, I'm not talking flood depths, I'm talking what is the possible components that are gonna get damaged from damage state 2. Like the drywall is gonna get damaged, you have to replace it. The appliances, the furniture, so that's damage state 2. But if the water is here and everything got damaged in your home, that's extensive damage. If your building is submerged with water, that's complete damage. So we need to find a component that contribute to each one of these. And how we can do that, like if you guys remember, we had like a 100 component here. We can group them, like this component is gonna contribute to damage state 0. This component is gonna contribute to damage state 1, 2, 3, and 4. And then let's say I have a group of 4 components. Like let's say, I'm gonna say the walls, the foundation, the roof, and whatever, something else, like 4 components here. I'm put them here because they need a higher flood depth to be damaged. So they are maybe at flood depths equal to 5 meters or something. But the appliances and everything is here, but I'm not interested at, that's the damage state 4. If your foundation and walls and roof are damaged, that means that you got submerged with water, and that's you are in damage state 4. The thing is, I want to convert these 4 components to contribute to damage state 4. Like I want them to be one curve, something like this. And at the end of the day, I want to have this curve, something like this, flood depths and probability of failure, to be, rather than a 100 curve, to be like maybe 5 curves, like something, or 4 curves, something like this. This curve is going to represent damage state 1, this curve is going to represent damage state 2, damage state 3, damage state 4. All right? Rather than having 100 curve, I want to have the exceedance probability of each one of these damages states. All right, so let's say that these 4 components, component number 1, 2, 3, 4, contribute to this damage state. I want to do you guys know how can I convert this 4 into 1? What should I do? What process that I can do to convert multiple things to 1? Or I need one representative information. Like let's say that 4 of us is sitting here, and one of us is like 27 years old, 31 years old, 35 years old. And I want one number that can represent all of us. So we get the average, right? But sometimes average by itself is not enough. Why? Sometimes we need something that's called weighted average. Let me tell you something. If I take these 4 values and divide them by 4, the thing is, the probability of failure, let's say here, okay? This component has a probability of failure 80%. This one has 50%, 20%, 5%. I take all these 4 values and divide them by 4 so I can get 1. That's called absolute average. But the thing is, are all of them have the same importance? Like let's say this chair got damaged and my fridge got damaged. Let's take the average and get the probability of failure. It doesn't work that way. This chair is like $100. I can't trash it, but I can't live without my fridge. So the fridge has more importance than my chair. So maybe I can neglect the chair from, I give it 0 weight and I give 100% to the fridge. But the thing is how we can work this out, how we can find something that can represent this way. There is some people would say, I'm gonna do this based on the importance of the components to me. Maybe I would give them importance factor. That's one way to do it. But I believe the best importance factor that we can use is the replacement cost of the component. Because that's just gonna tell me if this is important or not. However, sometimes the replacement cost is not enough because some components you can go and buy them in the same day, but some of them you need to have a contractor and have a permit and have people come over every day for a week, and it takes time to replace this drywall. It's gonna take a lot of time to do it, right? So that's also another factor, but let's not look at it, but keep it in your mind that maybe not replacement cost is enough, and I have to include the recovery time of the component. When I did my research, I didn't consider recovery time, but that's also a good point of research. If you included the recovery time into the fragility, and how important is every component into the fragility. Okay, let's only consider the cost. So I can get a weighted average, like let's say, I want one value, the exceedance probability, let's write it that way. I'm gonna say, the probability of exceedance is going to be equal to, all right, I want this 4 values to represent one value here. So I want to get this value, all right? And the same flood depth. Let's say a flood depth equal to 6 meters. To get this value, the probability, the exceedance probability at x equals 6 meters, so I need the summation of these 4, but I'm going to take I need the probability of failure number 1, number 2, number 3, number 4. So this is going to be equal to the probability of failure of each one of them, I, number 1, 2, 3, 4, multiplied by the replacement cost of number I over the total replacement cost of the whole damage state. Like let's say this component 1,000, this component is 5,000, 6,000, and this is 10,000, and the summation of all of them is 22,000. So I'm gonna put 22,000, component number 1 is 1,000, so it's gonna have less weight. But component number 4 is 10,000. So 10,000 over 22,000 is gonna have more weight, so this number is gonna be much more important. And then once I get their weighted average, I'm gonna get one single number, I'm gonna put it here. And I'm gonna do this for each flood depth, so you are gonna get the exceedance probability of each damage state. That's one way to do it. There's other ways in the literature that they see how they can convert the components damage into building damage, all right? So this is component fragility. This is building fragility. By the way, this is really, really important concept. If you know actually how to do this stuff, you are gonna do an amazing research. There's lots of fragilities hasn't been developed till now. But if you understand this concept, you can do a lot of stuff. Did you guys understand this concept? Okay. All right, let's say I was able to do this. By the way, I only showed you how to get one damage state. Let's say this is damage state 4. You are gonna do the same thing. I'm gonna show you next time when I get that adapter on the code, how to do this by coding. But you need to understand this concept so that you can do the coding, okay? All right, so let's say that we did this for damage state 4, and I put it here. For damage state 3, damage state 2, damage state 1. I need you to understand some concepts about these damage states, how to read them. Okay, if I want to read this damage states, like if somebody gave you fragility or you are reading fragility into a paper, this is how you read them. If you get, for example, at flood depths equal to 2 meters, and I hit this fragility like this, you guys tell me, what is the exceedance probability of damage state 1?
100%.
100%. Look, I'm hitting the 100% here, 1. Let's say this is gonna be, for example, 0.9, this is 0.3, and this is 0.1. The exceedance probability of damage state 2 is 0.9, the exceedance probability of damage state 3 0.3, and the exceedance probability of damage state 4 is 0.1, and that makes sense. Let's say 2 meters hit a building, 2 meters is not enough to make complete damage. So the probability of having complete damage is 0.1. But the probability of having slight damage is 100%. 2 meters definitely you are beyond the slight damage. But the probability of having moderate, it's still high, 0.9%. Extensive, it's 0.3. Okay? So that's how you read fragility. There is another way to read fragilities by the probability of being in a damage state. Okay, let's see what is the difference between exceedance and being in the damage state. If you exceeded damage state 2, like let's say, if you exceeded this damage state, that means that you already exceeded damage state 1. So, like, there's just a few things in the literature that you can exceed damage state higher, and the damage state lower is not exceeded. But I'm not gonna talk about it right now. But in general, if you are in a complete damage, so definitely the slight damage passed. Like your building is already wholly damaged, the whole thing. So it's complete damage, so slight damage is already 100%. Okay, so that's the thing that you put in your mind. The thing is, here, 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 and here, and here. All these, if you get this value, and this value, and this value, and this value, and you sum all of them together, how much is gonna be? 100%. So your 100% probability is divided between all the probability. So this building has 100% probability it's damaged, okay? Let me put it in a way that we have done it before. You guys remember the sample space? There was something like this, and that's your damage, all right? This damage, part of it came from damage state 1, part of it came from damage state 2, damage state 3, damage state 4. So let's say this is DS4, this is DS3, this is DS2, this is DS1, this is DS0. That means there is no damage, okay? So this is the pieces that comes from each damage state, right? the exceedance probability, when I say what is the probability of exceeding damage state 1, that means this and this. Because you already exceeded 0 to get to 1. The probability of exceeding damage state 2, that means 1, 2, and 3, all these pieces. The exceedance probability of damage state 3, so all these pieces. But the probability of just being in one damage state is just this piece. I don't care about the other pieces. Which means I'm just interested in this part. Okay? This is your 100%. This is your 100% damage. Part of it came from different damage state. So if I found this value, let me shade one of these. I'm gonna shade this part. This is the probability of being in damage state 2. All the area in between this curve and this curve. And here, this is damage state 3. Here is damage state 4. And let me put this as damage state 1. Alright? So the area in between the two curves are the probability of being in the damage state. Alright? Okay. So you have a part coming from this damage state, and a part coming from this damage state, and a part coming from each one of these damage states. So if you want to find, for example, right now I'm talking about the probability of being in a damage state. I'm gonna call it the probability of damage state 2. By the way, this is exceedance. This is the probability of being. Is equal to, look, is equal to this, the probability of exceedance of damage state 1 minus the probability.
2.
Oh, this is 2.
Minus
Sorry,
3.
yeah. This is 2.
Minus
3. Exceedance probability of damage state 3. This minus this is gonna give you this. But let me ask you, right now you know that there's contribution from each damage state, but what is the most probable damage state? What is the dominant damage state from all these three?
The largest one.
Is what?
The largest one.
DS1.
The largest one. DS.
Yes, 3.
Yeah,
Okay, let me tell you. There is the probability of being in damage state 1 is 10%, 1 minus 0.9, right? This piece. The probability of being in damage state 2 is 0.9 minus 0.3 is 0.6. The probability of being in damage state 3, 0.3 minus 0.1 is 0.2. And the probability of being in damage state 4 is equal to 0.1. So the most probable damage state is the one that has the higher probability of being in the damage state. So that is the most probable damage state. Like, because the thing is, when you go to assess a building and you go to tell the homeowner, or you are talking in a meeting, you are not going to tell them, oh, this building has a probability of this for damage state 1, and damage state 2, and 3 and 4. They don't care about this. What is the damage of the building? How we can give one designation of the building. So if you need only one designation of this building, I'm going to tell that this building is damage state 2 and has moderate damage, because this is the most probable or the highest probable damage state. So look how we get this. The thing is, a flood hazard hit a community, damaged all the buildings. We need to give one designation for each building. Look what we did. We get component fragility, and from the component we get building fragility with the weighted average concept. Then for every building we try to find, like, let's say a building got a 2-meter flood depth. We found the exceedance probability of each damage state, and then we found the probability of being in each damage state, and then we found the maximum, and based on the maximum we tell the homeowner your damage state is, your building is designated as a damage state 2. Okay, and that's what we have done here. Okay, did you guys understand the process? If there is any confusion, just ask me, because this is the base that we are going to build on when we are doing our coding next time. So we understand that? All right, so that's for just one building archetype. That's for just one building. Like, let's say when we started here, I picked one story on a crawl space foundation building, and then I divided it into components, and then I did this whole process to come up with this fragility curve. But let's say I want to do community level analysis. let's get back to the first lecture. We use the concept of building portfolio. We develop a portfolio of like, I don't know, 15 building, 20 building, 100 building, whatever the number that you can do, and do the same process for all the building within the portfolio. The thing is, this building is 1 story. If you take this fragility and you put it on a 10-story building, it's not gonna work. It's gonna give you misleading answers because it has other stories. So this archetype, when you are gonna use it, you have to use it with an archetype that is matching. And definitely, there's no way that this archetype that we are using is gonna match the building that you are studying 100%, right? Because we developed this archetype from our imagination. A residential building has 3 bedrooms, 2 bathrooms, whatever, but other buildings are gonna be 5 bedrooms. There will be slides. The thing is, that's why we included uncertainties. Do you guys remember? We put upper and lower bounds and all of these stuff. But the thing is, when it comes to fragility, as soon as the building 1 story, and let's say you added, the thing is, the more bedroom, the more appliances, the more furniture, right? But the thing is, they having one thing in common. All the furniture are almost having the same elevation. If you have 3 beds and 5 beds, they are all having the same elevation. We are not looking for cost, we are looking for damage. So they are having almost the same elevation. So you will end up having almost the same fragility. If you want to try it, like if you want to use this, that's actually a perfect case study. If you want to do research, like you might pick 5 or 10 residential buildings that have different characteristics. Because what I did in my research, I picked only 1 that has that like this. But let's say I'm gonna pick 10 of these. 1 of them 3 rooms, 1 of them 5 bedrooms, 1 of them 2 bedrooms. And I'm gonna develop fragilities for all of them and see if they matching or not, and what is the difference. And is it really huge difference that it needs all these archetypes? It's intensive to do it, but it's one way to prove yourself that maybe 1 archetype can represent these all 10 archetypes, and you don't have to develop more of them. So yeah, that's one way to look at it. But this concept is very, very important, and it's very good base for what we are gonna do next time. So next time I'm gonna solve this issue. I believe I forgot, or last time when I was using this, I forgot my adapter. So somebody took it, and I'm gonna get a new one, and then I'm gonna show you on the MATLAB code how we are gonna do this step by step, okay? All right, maybe I'm gonna send you a video on the MATLAB code. Maybe you watch it before the lecture to get prepared on every step that I'm gonna do, because it's a very, very long code, maybe 400 lines. So if you wanna be ahead of the game, maybe you watch this video and then you come here with questions that you didn't understand from the video, but I'm gonna explain it. But while I'm getting to each step, oh, I watched this step yesterday and I don't understand this part, so we can talk about this part more, okay? All right, sounds good. See you guys next week. Really? These fragilities is really